Very absent-minded. Sometimes forgotten to record. Okay, the first question to start. I hope you have tried that. Try this one.
Yeah.
What's the answer?
So which dog is this?
269.
Pardon? Page
Page
269 of the medical. Okay.
number 12. 270 there lah. About there.
269.
You have to correct for background radiation first lah. Background is 20 lah. What's your answer?
15 days.
First thing, we need to subtract the background count rate from the reading. After 90 days, the count rate is background. This one is cannot use because it is background radiation already. So 60 minus 20 is 40 for the first for 10 days. And then for 30 days, 30 minus 20 is 10. So 40 to 10 is 2 half-life lah. 40 to 20, 20 to 10, so 2 half-life lah. So 2 half-life, 2
Oh,
times
10 days.
10 days lah. A. Okay. The rest you can try yourself lah. Okay, this is question 2011. You must know how to read the graph, no? And where to put the variation with nucleon number A of the binding energy per nucleon is shown in the figure. Mark the appropriate position of iron 56 at the top there. Lor. So zirconium is about 97, so about there. Lor. The hydrogen is at the first one. Lah. Deuterium is the first one. Lah. And uranium is the last one on the curve. State what is meant by nuclear fission. Yep. What is meant by nuclear fission? Yeah, muted.
When two nucleus split into two or smaller nuclei,
No,
releasing large energy.
it's a heavy nucleus. Heavy nucleus breaks up into two nuclei of approximately equal mass. It's a smaller mass. By reference to figure 8.1, explain how fission is energetically possible. Yep. How is it possible? By referring to the graph. Right? That's the graph. How is it possible? Fission occur here. Usually take place for the reactants here. Binding energy of nucleus, right? Is binding energy for nucleon times A. Binding energy of parent nucleus is less than the sum of binding energy of fragment. Okay, that's all. Okay or not? 2 mark.
Yeah.
State what is meant by binding energy of nucleus. Remember?
The energy required to disassemble a nucleus into its individual protons and neutrons.
Energy required to separate the nucleons in the nucleus to infinity.
To
Or
infinity.
completely lah. Or completely lah. This one show you should be able to do that lah. Okay, we have done in class. So you go to look at your data sheet. One atomic mass unit is 1.6 and 10 to the power minus 27 kilogram. Then E equals to mc square. Right? M is that one. And speed of light, square that. You got this one is in joule. Convert it to mega electron volt. Right? A mega electron volt is 1.6 and 10 to the power minus 13 joule. Right? Divide joule by 1.6 and 10 to the power minus 13. You get 930 mega electron volt. Any comment? Or anything still not clear? Can? Can or not? Or which step you don't agree?
Okay.
Okay. Data for masses of some particles and nuclei are given in figure 8.1. Use your data from figure 8.1 and information from B to determine in mega electron volt the binding energy of deuterium. What's your answer? Calculate the mass defect first. Total mass of nucleon minus total mass of nucleus. Total mass of nucleon. Total mass, then mass of the mass of deuterium. Subtract that in atomic mass unit. So you get 1.9 times 10 to the power minus 13 atomic mass unit. You're supposed to determine in mega electron volt. So you have to derive it, then convert it on. And 930, 1.8 mega electron volt. Can? Any comment?
Yeah. No.
Binding energy per nucleon for zirconium. Same, no? Total binding energy, total mass of nucleon minus total mass of nucleus. Right? Got 57 neutron. And mass of neutron. And 40 proton. And mass of proton. Minus your mass of zirconium. And times 930 for nucleon. You have to divide by number of nucleon first. And then convert this one to mega electron volt. Right? And 930, I derive that. Divide by 97. Got 97 there. Can?
Yep.
Okay, good. Okay, radioactivity. This one is 211 October, November lah. Paper 42 lah. Isotope phosphorus undergoes beta decay to form sulfur, which is stable. The half-life of phosphorus is 24.8 days. What is half-life? This one you need to remember lah.
Half-life is the time taken for nucleus to decay to half of its original mass.
Okay, good. Time for initial number of nuclei or activity to reduce to 1/2 of the initial value. Show the decay constant. So you should be able to show that using the formula given 0.693 divided by T half, 24.8 days. Change the 24 hours. 1 day is 24 hours. 1 hour is 3,600 seconds. Okay.
Okay.
A pure sample of phosphorus 33 has an activity of that. Calculate the initial number of phosphorus 33 nuclei in the sample. Got the answer? Yeah, just getting you to use the formula that you're supposed to know, remember. N naught times lambda. Right? And now you have already calculated. Oh, sorry, lambda is given. N naught. And then this is the activity. Okay, number of phosphorus nuclei remaining in the sample after 30 days. Right? Just use the formula. Right? N naught, that's the original number. N naught exponential. You can use 0.693 if you want. You need to use ln 2 times T is 30 days. So we are just using T times ln 2, T half. Right? You want 30 days, so we use 24.8 days, so half-life. Yep. Is that the answer that you get? Ken, anything not agree?
Yeah.
You can use this formula rather than ln 2. I calculated all this value. After 30 days, the sample in B will contain phosphorus 33 and sulfur 33 nuclei. Use the answer to calculate the ratio number of phosphorus nuclei after 30 days, number of sulfur nuclei after 30 days. What is your answer? Right? Number, that's the number of phosphorus original, and the number of phosphorus becomes a number of sulfur. Right? Common factor is 10 to the power 13, 1.15 original minus what is left. Okay, Ken?
Yeah.
Okay, last question. Radon-222 is a radioactive element having a half-life of 3.82 days. Radon-222, when found in atmospheric air, can present a health hazard. Safety measures should be taken when activity of radon exceeds 200 becquerel per centimeter per cubic centimeter of air. Define radioactive decay constant. That's the first part. Memory work. Right? Should be able to score that. Probability of decay per unit of nucleus per unit time. Show right? Should be able to show that, right? It's just a repeat. Lambda T half is ln 2 or 0.963. Right? We are changing this to second. Right? Yes, okay. Can anything still not clear?
Yeah.
A volume of 1.0 cm3 of air contains that amount of molecule. Calculate the ratio of number of nucleus in 1.0 cm3 of air to number of radium atoms in 1 cm3 of air. Right? So refer to what is given. These are all that's given from the previous question. For the minimum activity of radon at which safety measures should be taken. Right? Activity is lambda times n. Right? There's a lambda. 200 times lambda. Want to find number. It's 9.5 times 10 to the power 7. Ratio. Okay, 2.5. Right? That's the one. Over 9.5%. Can? Is that the answer that you get? Or anything you still need to explain further?
Okay.
Okay, that's about all. Let's go to X-ray again. Okay, production and use of X-ray 291. Right? Very straightforward lah. Your syllabus explain that X-ray are produced by electron bombardment of metal target and calculate the minimum wavelength of X-ray produced for the accelerating PD. That's all. So we are going to cover this one, but a lot of things I teach will be extra lah, just for knowledge lah. Right? Partly because I see if you teach that, how are you going to understand what's happening? Okay. Since we have started, let us go to okay. Function of components of X-ray tube. Right? This is your info only. Not all are required for your syllabus. Right? If you are interested, YouTube, there are some YouTube that you can follow up. Okay, there's your X-ray YouTube. Right? You don't need to know at all. You just need to know that voltage and the electron is emitted from here. Okay, evacuated chamber. Vacuum ensures that the emitted electron accelerates the target. You don't want the electron that's emitted here to be scattered all around by the air molecule. You want it to go straight to the target. Low voltage, purpose to heat the filament, or the filament is our cathode lah. And this high voltage or accelerating voltage, right? High voltage, usually 20 to 100 kilovolt, or sometimes it's called accelerating voltage because This is the cathode. This is the anode. So you accelerate the electron to hit the target. That's the target. And positively charged. Positively charged. This is positive. This is negative. Right? That is the target. As the electron is emitted, hit the target. And the X-ray is produced coming out of the window. This is a window. X-ray window. Allow the X-ray to come out. And a lot of heat is generated in the target. So if you don't remove the heat, the target will melt out. Right? The anode will melt out. So cool metal anode, you have to cool it down. Right? This one, high voltage provides the operating voltage, accelerates the electron. Low voltage source for heating the cathode is negatively charged usually. Controls the filament current. Control the current. Control this current, the electron that's hitting the target. Electrons are emitted from cathode by thermionic emission. Determine the density, intensity of the X-ray. Electron decelerate, right? Interact with the target, decelerated and lose energy to the target. As usual, you need to remember this formula. Energy given to electron, right, is accelerated by a potential. Between that, so that's your accelerating potential. There's a charge of electron. Put on energy given to electron. And this one determines the maximum energy of X-ray that can be produced. 1% of energy of electron appear as X-ray. So it means that 99% will hit up the target. That's why you need to cool the metal target anode. Heat produced by decelerated electron radiate as heat. So that heat has to be removed by cooling the metal. Low voltage source for heating the cathode controls the filament current in the tube at a given operating voltage and controls the intensity of the emitted electron. Right? Depending on the current, the amount of electron emitted is controlled by that low voltage source. Anode is positively charged. Anode is positively charged. It's made of solid copper, white copper. Copper is a good conductor of heat. A lot of heat is generated in the X-ray tube. About 99% of the energy of electron is converted to heat. Purpose of the accelerating voltage is to accelerate the electron emitted from the cathode. That's the cathode. Target is usually tungsten as it has a high melting point, and as a heavy metal, the nuclei interact strongly with bombarding electron to produce X-ray. Right? So the electron will hit the target, the X-ray is produced. Cathode is negatively charged. That's right, a negative accelerating voltage. It's connected to the anode through high potential or accelerating voltage. Electrons are emitted at the heated cathode, thermionic effect, and accelerate to the anode. Right? Electron is emitted at the cathode, accelerated to hit the anode, the target there. High voltage unit, this one, or accelerating voltage. Right? High voltage or accelerating voltage. Your syllabus call it accelerating voltage. Source of high potential difference, right? Is an external power unit applied between the cathode and anode. provide the accelerating voltage, provide the operating voltage, sorry. There's a PD accelerates the electron to a very high energy before they strike the anode. So maximum kinetic energy of electron is EV, where the voltage is V here. Cooling fins, heat generated at the target is conducted along the anode to the cooling fin. Cooling fins radiate away the heat. Right? There are various methods of cooling the target. We won't go into that. Okay, let's go to energy of electron. High voltage. There's high voltage unit, there's capital B. Kinetic energy of electron on reaching the anode, that's the maximum that it can receive. V is the operating voltage or PD across the cathode and anode. Right? The kinetic energy maximum will hit the target, cathode target. This is required in your syllabus. Right? It's required. Energy of X-ray photon, HF, equals to EV. That's the energy of the electron. But some of it is lost as heat in the target. So there is a frequency of X-ray photon, F. Lambda can be calculated from C over F. Right? This is done on the electron, or the maximum that the electron can get. And this is the energy given to the target as heat. Maximum frequency of emitted X-ray, right? Where this Q becomes zero, or the energy of the electron is given to produce a photon. And all the electron energy is given to produce a radiation. This gives the minimum wavelength. Remember, maximum frequency, minimum wavelength of X-ray. H is Planck constant, C is the speed of light. Right? That is the formula that you likely encounter under modern physics. Emitted electrons emitted by heated cathode are accelerated through a large potential difference of between 20 kilovolt to 100 kilovolt for diagnosis before bombarding a metal anode. The X-ray produced leave the tube via a window. Where's your window? It's going out from the window like X-ray. This for information. Intensity of X-ray beam is determined by rate of arrival of electron, number of electron here, rate of arrival of electron on target there. This is controlled by the low power source. Thus, intensity of X-ray beam can be considered as the number of photons of specific energy emitted per second per unit area. Okay, the X-ray is produced and coming out of the window here. So we can see intensity of X-ray beam can be considered as the number of photons of specific energy emitted per second per unit area. Right? Remember that's our intensity in terms of particle. We think of radiation, X-ray radiation as a particle. Number of X-ray photon, energy of photon, area, cross-sectional area, that's the time. The tube current is controlled by heater current of the cathode ray. This is the one to control the tube current. That is the tube current. Right? That's the electron beam. The greater the heater current, the hotter will be the filament, and hence the greater the rate of emission of the minor emission. Right? All these are for your info only lah. You won't be tested on that. Right? The hotter this is, more electron is emitted. Lah. The more electron, more photon of X-ray are produced. Lah. Okay, this is also for info only. Right? There's a spectrum of X-ray with a minimum wavelength, and then the range can be from minimum to the longest wavelength, shortest to the longest wavelength. Spectrum consists of two components, namely a curve showing continuous distribution. Right? Intensity is different for different wavelength. With sharp spike, right? These are spikes, not in your syllabus, cut off at short wavelength, right? Cut off at short wavelength. Series of high intensity spikes. Right? There's continuous energy. These are your spikes. And then it cut off at minimum wavelength. That's all you need to know how to calculate that. That are characteristic of the target material. Right? The spikes where it occur depend on the target material that you use. Right? This one summarized for you. Don't need to know about too much. Only the minimum wavelength, how to calculate that. Okay. We won't bother about the others. Right? There's a metal target. There's an electron hitting the target. We are just reviewing what we have learned. When high speed electrons strike a metal target, large deceleration occurs and radiation produced is in the X-ray region of the electromagnetic spectrum. Since the electrons have a continuous distribution of acceleration, you can lose any amount of energy. That is, they can give any amount of energy to a maximum energy, any amount to a maximum energy. A continuous distribution of wavelength of X-ray is produced. That's our equation. Ek max, energy of photon plus Q. F max is when Q equals to 0. Right? So that is where you calculate your cutoff wavelength, the minimum wavelength. EV equals to 8F. The minimum wavelength is, replace this one by C over lambda. Then lambda take across there, take EV down, you get this equation. Okay, that's how you calculate your minimum wavelength. Any comment or anything that's not clear? Anything you want to ask?
Okay.
So the wavelength is continuous. That's all we know. From minimum wavelength to large wavelength. So minimum is where all the energy of the electron is given to produce the X-ray. At the cutoff wavelength, the whole or the energy of the electron is converted into energy of one photon. Okay? That's the minimum wavelength. Now to derive it, and these are all repeating. Low voltage supply the X-ray tube. So the intensity. Right? Basically, this low voltage source hits a filament. They produce the electron, and the electron is the one that hits the target. So how hot it is? If it's hot, it will produce a lot of electron. then it affects the intensity. Dislocating electron can give all or part of the energy to the target. The larger the energy of the electron, the larger the energy of the X-ray emitted, and thus the shorter the wavelength of X-ray. X-ray generated has a range of wavelength from minimum value to as high as possible. Okay, we won't bother about all this. Anything that is not clear. Yep, anything that is not clear. Anything you want me to explain?
Okay. Everything's alright.
You'll be cut off at any time now lah.
Still have 2 minutes.
Yeah, about two more minutes. Okay, penetrating power syllabus also not mentioned. Penetrating power is the ability of radiation to penetrate matter. The greater the energy of the X-ray photon, the further they are able to penetrate through a material before being completely absorbed. Right? Greater energy, greater penetration can pass through the material. Quality of X-ray is the hardness of X-ray. Quantity of X-ray is the intensity of the X-ray. Hard X-ray, hardness, hard X-ray are X-ray with high penetrating power and hence high photon energy and frequencies. Right? High photon energy means high frequency. Right? So the tracking voltage is 100 to 150 kilovolt. Used to investigate bone fracture, X-ray are attenuated, absorbed by the bone tissue, but suffer little attenuation by soft tissue. Right? This is hard X-ray. Absorbed by very little by soft tissue surrounding the bone. Right? Attenuation or absorption or reduce in amplitude. That's what attenuation is all about, reduce in amplitude. Soft X-ray are X-ray that have much lower penetrating power and hence low photon energy and frequency. Frequency is 50 kilovolt. The exciting voltage. They have longer wavelength. Soft X-ray are unable to pass through patient, contribute to total radiation dose without any useful purposes.